So the topic of today's session, which is a repeat of an earlier one, is what is VM teleportation? Now, I wanted to just ask an interesting question. Did anyone here go to TA8051-Infrastructure, which was Jay Judkowitz and Kumar from VMware had a session? So if you didn't raise your hand, man, trust. Did you dig it? Yeah. If you're interested in what's going on in storage land, I'd recommend checking that one out after VMworld's over. It kind of had the what's VMware's vision around storage, 3 to 5 years out, and had discussed many topics. But one of them was this idea of federated storage models, right? And it's an important idea for a lot of reasons, which we're going to be discussing. And we're going to be discussing stuff that's available now, do's and don'ts, practical things like that, as well as kind of previewing where we're going a little bit, because you come to VMworld to kind of see a little bit of the future as well as understand what's practical now. So, usual legal mumbo-jumbo. I'm not an expert in law, but there's going to be some stuff in here that we're describing that's futures, blah, 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 blah. Okay. And forget the agenda. So now, I want to set up the fundamental idea, because it's important to understand the fundamentals here as we dive down and down and down and down. So everyone here understands how VMotion works. It's magic, and it is magic. You move a VM around, but obviously the VMX files, the VMDKs, all of the stuff that VM is referencing, the information. And I thought it was actually, did anyone go to the 9 o'clock general session? I mean, that was pretty cool stuff, right? The one thing I thought was fascinating was they kind of emphasized that the information is actually the most important thing, right? Not how we interact with systems all in different ways, bless you. But information is actually the thing that we fundamentally use compute for, right? The information here, in this case, stays in one spot. Of course, everyone understands classic storage vMotion, which is also magic. Storage vMotion is fantastic. And what it involves is the VM stays still. All the VMware files, all the information moves. Memory state and all the data can move if you use both of them together. What VM teleportation is this idea that the compute moves, but the information is federated. Federated means that it's instantly accessible in many different places, right? So if you spread these things apart over some sort of distance, with some sort of distributed information model, you could then VMotion things willy-nilly anywhere, because the information would be simultaneously read-writable in many places at once. So that's what we mean when we talk about this VM teleportation idea. So let's dive down into this a little bit deeper. So why is this important? It's because what Paul said on stage in the keynote on Tuesday, right? Loosely described is this picture here, right? Inside EMC and our other partners. Obviously, it's a shared vision with VMware, and if you went to Cisco Live, you'd see John Chambers describe the same idea. We jokingly call it the three-legless sheep diagram, because you can see there's a legless sheep on the left. It's kind of fluffy, has no legs. That's the private cloud. That's the data center you build on your own. The public cloud is the other legless sheep, and then over top of it there's a hybrid cloud. The hybrid cloud is really most powerful if it was possible to move your workloads non-disruptively between your own private clouds and in and out of public clouds, right? The idea of being able to VMotion perhaps anywhere. So this is why this technology is fundamentally very important. And a very strong focus of a lot of engineering effort at EMC, at VMware, and around the whole technology community. So VPLEX is basically designed for this purpose, right? VPLEX is a federation platform. In other words, it allows data to be read-writable in multiple places at the same time. It's designed to solve problems around simultaneous access to information. It's designed to solve problems about non-disruptive mass data mobility, resiliency to unplanned outages, but more importantly to planned outages. In other words, what if I know I need to turn off my entire data center to do power maintenance? What if I see a hurricane coming, right, and I want to VMotion the entire data center, right? Those sorts of ideas. Now, if you take a look at it, VPLEX has been GA since April. And the thing that's GA is the idea of what we call VPLEX Local and VPLEX Metro. VPLEX Local is used inside the data center. You could basically have non-disruptive data mobility from non-EMC arrays to EMC arrays to non-EMC arrays, any combination of those sorts of things. For non-disruptive, array replacement, that sort of thing, the classic storage virtualization kind of use cases. But the other thing that we GA'd is the ability to do it across synchronous distances. So in other words, have a stretched distributed virtual volume across, we say, 100 kilometers. It's actually not, since this is a technical audience, you guys can understand, it's actually not measured in kilometers. It's measured in latency, right? So 5 millisecond round-trip latency type of circumstances is what that corresponds to. Many customers actually have, a given network connectivity where it could be longer or perhaps shorter, depending on what their latency of their underlying infrastructure is. But we also publicly committed at EMC World back in I think it was May, that we would be shipping in 2011 the ability to go across asynchronous class distances. So the technical problems and challenges that are associated with that are significantly larger. I mean, what we can do now is very cool, very unique, very magical, but then being able to extend that over longer and longer distances becomes addressable to much, much larger segments of the market and to many, many more customers. And if we take a look even further out, we committed that at some later date, this is VMware always refers to this as vSphere future releases, that sort of language, around the idea of VPLEX Global, which means that up till VPLEX Geo, you have 2 sites. VPLEX Global means that you have many sites. You have a larger number of sites. And the idea there is that eventually the whole idea of the physical boundaries of the data center we think are going to get very, very abstracted out. Make sense? So what's funky about VPLEX? What's funky about it is several things. First of all, it's an active geodispersion model. What that means is that literally the data looks like it's local on both sides all the time. This is different than things where it's an active passive model. In other words, you can non-disruptively fail over to the other site, but until you do that failover, all the data is really on one side and accessed over a stretched network. Here it's literally like the information is in both places at the same time. The second thing is that we designed it to be an N+1 scale-out architectural model. The thing that's important here, do we have any EMC customers in the room? So first of all, as always, thank you. If you're using a EMC Clarion or Solera mid-range array, or you're using a VMAX, they all actually run on the same x86 hardware, right? What we call a storage engine, right? Which in effect is a pair of servers, right? If you go to the booth, you can see them and you can look at them. People think of these storage arrays as being things that look like I put in the previous diagram. But really, that's a little cluster, right? What we needed to do here is we needed to say, look, if you're going to virtualize stuff, you can't stick something that's like a 2-node cluster, and that then becomes the I/O bottleneck. So it needs to have a scale-out design, which is important, as we'll discuss later. The other thing that's important is this idea of very large port count, very large distributed cache, and that's actually the fourth point that's very important, which is we've got the idea of what we call distributed coherent cache, right? Which means that's the thing that powers this idea of the information being accessible in both places, sometimes even if the actual bits aren't there. So this is a weird idea, right? But a configuration that actually is supported is a case where you have the VPLEX nodes in your primary data center, and the other half of the other vSphere, the other VPLEX cluster is sitting in another data center. This one has all the storage. That one is basically just doing a cache and forward back to the primary data center. So you can imagine various use cases for that. But the key thing is that coherent cache is this thing that enables initially sync distances and then over time asynchronous class distances. Now, and that's the thing that I think is very important. Every technology that is designed a certain way has certain challenges that will impede its ability to go to a future state. So in other words, what the engineers are thinking of when they build the product for the first time, dictates what V2 and V3 and V4 are going to be like to a certain degree. VPLEX, while it's been GA since April and has many customers, has actually been designed for VPLEX Geo and VPLEX Global, right? So, does anyone here do data replication today? So replicate to another site, right? Often people look at this, and since we're describing something that's a little bit funky and new, people look for mental analogies to kind of help them go, okay, what exactly are we talking about? And they first think of data replication, right? Data replication today always has a model where you have one side that has a copy of the data, and then it's being replicated via synchronous replication or asynchronous replication or even continuous data replication approaches. But it's in a read-only state on that side. The way you make it readable is by breaking that replication state or taking a snapshot of that remote side and then making it read-writable, at which point it's now different than the primary side. Right? That's replication technologies that exist in the market today. VPLEX has this idea where literally it's one volume that exists in both places. It's a very, very different idea. And it's an active-active model. So what does it look like? If you take a look inside one VPLEX engine, it's composed of an HA design. So in other words, another thing that we take very, very seriously is this concept of how do you build a highly available infrastructure, right? It's something that's important to our customers, obviously. Each node in a VPLEX cluster is inherently, HA. Consists of two engines, consists of two directors, and like all EMC platforms, they're all based on multi-core x86-based designs from Intel. They've got a very large number of front-end ports and back-end ports, and then there's this thing here, which basically is designed for intra-cluster communication, because you could have one of these, two of these, three of these, four of these inside a single cluster. So, today it's front-ended via fiber. Over time, there will be additional interfaces on the front end. Loads and loads of back-end connectivity to the underlying storage arrays, which again can be EMC or non-EMC arrays, and lots of cores, huge distributed cache, and then these things that connect to the other cluster nodes. What VPLEX does is it has a hierarchy of virtualizing the underlying storage. This falls in the category of virtualized storage products. Underneath at the bottom, you've got these idea of the actual storage arrays present up stuff that gets turned into these devices that can span across multiple things and then are presented out to hosts. Right? So there's a hierarchy. And the only reason I put this here is, has anyone gone to the EMC hands-on labs? Was it good? Yeah. So there's an EMC hands-on lab in the actual EMC booth. Has anyone gone to the actual VMware hands-on labs? If you haven't, man, you're missing out. It's pretty cool stuff, powered all over the place. The one thing that happens in the VMware hands-on labs is they androgenize all the underlying infrastructure stuff, which is cool. Like, our job in those things is to support VMware, not make, hey, look at the cool thing we can do, right? Although one thing that will be cool, if you're a reader of Virtual Geek, after, is anyone here a reader of Virtual Geek? A few. Thank you. At the end of VMworld, we're going to be posting all sorts of stats of the underlying infrastructure that powered all the hands-on labs once the whole thing is done and closed, which is mind-blowing stuff. But what we wanted to do is we wanted to have a place where people who were interested, or EMC customers, or interested in how this stuff works, could try plugins and stuff like that. And you can actually try, VPLEX there yourself if you're interested in seeing how this works. You go through the process of constructing these distributed volumes. Now, the way it works, and again, since I am kind of fundamentally an engineering type, I think this is kind of cool. This explains how the cache coherency model works. So let's say that you have two directors that are now sitting in one individual storage engine that's sitting in one place. And a read comes in. So a read comes in, hits that virtual volume, and says, hey, do I have this in my local cache? No, I don't. I'm going to go out and find out because I've got a map of where all of the cache is across multiple distributed nodes. I'm going to get that data. I'm going to suck it back to the one that originally captured the request, issue that read. Read goes across, gets the data, loads it into the local cache. So now, which is a higher likelihood that that'll also be hit again in the future. And then it responds back to the original host request, right? Another example is a write hit. So let's say that you want to issue a write. Write comes down and says, hey, look, do I have that data locally? If I don't, is that data globally available? Okay, great. I'm going to invalidate that prior one because the write cache needs to always be the current write data, right? So I need to update it wherever it is. I should store it locally because it's likely that I'm going to have to do this query again in the future. And then I'm going to actually write it to the SAN and be done. Now the reason, I'm going to pop back one. The reason, if you understand this idea, you understand the beginning of the magic, because you could, in theory, split that thing. Of course, you don't split two in a single HA cluster, but since you could have multiple storage engines, you can geographically disperse those. Now, an important idea that people don't immediately get is that what this means is that the information looks local even if it's not local, right? The reason that's important is that when you VMotion the individual VM, the data doesn't exist there necessarily until you do the VMotion. And obviously people don't want to VMotion data stores. They want to VMotion individual VMs, right? So the unit of VMotion in this case is the set of blocks, actually 4K underlying blocks that are in the cache itself. So, and by the way, in case people don't immediately grok why that's important, let's say that you're using your private cloud and you want to send your 100 gig VM to the public cloud. How long is it going to take you to get that 100 gig VM there, right? Wouldn't you ideally want it to VMotion immediately and then the data to trickle over after the fact, right? Because you want the VMotion to be quick, and if you extrapolate that out to not one VM with 100 gigs, but let's say you want to do that for a much larger data set, that problem gets bigger and bigger and bigger and bigger, right? You can try and address it with like WAN compression and WAN optimization techniques, but fundamentally, one thing that's important is the idea of data accessibility before necessarily the data is there. Does that make sense to everyone? All right. I think we'll probably have enough time at the end that if there's Q&A, I'd love to get input, questions, anything. So, very important idea here is scalability, right? So this is actually a test that we ran with an OLTP workload where we started with 2 nodes in the cluster, so 2 directors, right? And then scaled up to 4 nodes and then 8 nodes. And you can see that the workload was pretty linear as we continue to scale up the number of nodes. Again, this is really important because if you're a big customer and you put this thing in front of your storage array, it can't become the bottleneck, right? Which is why these scale-out designs are fundamentally important. The other thing that you want to do in case you're putting something in front of a storage array, in effect, is how much latency is going to get introduced. There's always some latency that gets added, but you can see here that it's pretty darn small. It's about 200 microseconds. And storage array latency is normally in milliseconds, right? So very small of additional latency. Now, I'm being a little conservative here. I could have actually put up another slide. We did some testing where the caching actually improved performance, right? Because you've got a larger distributed cache there sitting in front of an array that doesn't have as much oomph. Now, at EMC World, we did a demonstration of this, and the demonstration that we did live on stage. It was pretty cool. And prior to EMC World, I'll tell you a little bit more about that one. We did a test where we had an EMC array and non-EMC array separated by 100 kilometers. We created distributed virtual volume across those 2 arrays. And then we did a series of tests to see how does it work if you just do a storage VMotion and then a VMotion? How does it work if the data doesn't exist there before it gets there? And then how does it work if there's an underlying synchronous copy of the data? So here we used no underlying federated storage magic, right? So literally we said, okay, let's just do a storage vMotion of the VM across the 100 kilometers, hit the other array target, and then once it gets there, do the vMotion itself, right? Has anyone here done a storage vMotion in their life? Good. And if you haven't, give it a whirl. It's pretty cool. It takes a certain amount of time, right? And the vStorage APIs for array integration hardware assist that. There's lots of good things about that. But the larger the amount of data, the longer it's going to take because it's physically copying and moving a boatload of data, right? So here what occurs is we started the storage vMotion to the other storage array 100 kilometers away. You can see that it increased the guest level latency, right? Because the storage array is a little more busy while it's doing the work. And roughly 2 hours later of these 5 VMs being storage vMotioned, the storage vMotion finished. Now, if that strikes you as a long time period, it's not. Most people do storage vMotions locally, right? When you do it over a longer distance, the incremental latency makes the entire operation longer and longer and longer, right? And at the end, once the data was over here and the VM was out over here, we just did a vMotion, which, like most vMotion, takes time scales in the orders of tens of seconds. Make sense? How big were the VMs? I believe that they were about 200 gigs a pop, right? So the next thing that we did is we said, okay, let's set up the distributed virtual volume, but not replicate the underlying data in the arrays, right? So in other words, do the vMotion and immediately say, now create the distributed virtual volume, and the data actually starts to get sucked over. So boom, we establish the VPLEX mirror starting, and we do the vMotion. Immediately, the vMotion ends, because the VM immediately thinks that the data is over on the other side, even though the data isn't, right? What occurs then is that for the next, 40-odd minutes, the data is being served up by this cache forward and proxy and being sucked over as the underlying synchronous copy of the data exists on the arrays on both sides. Does that make sense? So you can see, as you'd imagine, that basically as more and more data gets sucked over, right, the latency gets better and better and better and better because more and more of the data is actually not needing to be read across the wire and sent over. This is a manifestation of that thing that we were talking about, of the data being accessible anywhere, even though the data itself may not be there yet. Does that make sense? One thing that's interesting is you'll notice that at the end, the latency is actually a little bit lower than it was before. Why? Because of the caching model, right? A much larger cache copy of the data exists at that point. Now, the place that we see this being used the most commonly today is this scenario. A customer has 2 data centers already set up. They create their underlying VMFS volumes out of the gate as a distributed virtual volume that has a mirrored copy of the data on both sides, at which point vMotioning those 5 VMs looks like this and ends like that, right? So in the span of 100 seconds, we now vMotioned across 100 kilometers. Does that make sense? Now, for those of you that are Virtual Geek readers, I'm not just perpetually plugging the blog because I want to take over Duncan Epping, who writes Yellow Bricks, which is blog numero uno, and I'm number 2. Yellow Bricks, yeah. Never heard of it. Duncan's blog is very, very good. It's also a good way for me to have an ongoing dialogue with you guys as VMware customers and customers of EMC and other folks as well. At EMC World, what we did on stage to kind of highlight how this works is we did a vMotion between Boston and Hopkinton, which is EMC headquarters. For those of you unfamiliar with Massachusetts, that's going where MIT, where all those cool people we saw on stage were, roughly around call it 60 to 70 kilometers away, right? And we vMotioned 500 VMs in the span of 15 minutes, lifting up in effect the entire data center, moving it over from one place to the other. And for those of you that did see that, we did it with a little vCenter plugin that had a little button that said vTeleport, right? So it said vTeleport from Boston to Hopkinton. So, and it was cool. It had a picture of the clouds and the VMs going toot, 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 over like that, right? Now, we mocked that, the vCenter plugin that was actually real right? It was actually using the vCenter APIs to read where the VMs were and how they were moving. But there actually will be, very shortly, for EMC customers, via our vCenter plugins, a real vTeleport capability within vCenter. So if you're an EMC customer, again, just raise your hand. Keep your hand up if you are using our vCenter plugin. If you are not, please come and talk to anyone wearing one of those blue shirts. Guys, stand up if you're wearing the, please talk to them. The vCenter plugins are free, right? They allow you to provision storage directly from within vCenter. They allow you to see the relationships of VMs to underlying storage and all that stuff, right? They allow you to compress VMs and do all sorts of cool stuff. Right? Again, did I mention they were free, right? And VMware admins want to provision stuff themselves. They don't want to have to talk to other people within the organization, right? So, hey, you can use that. That thing's always evolving. We're currently at VSI, which is the Virtual Storage Integrator version 3, Virtual Storage Integrator version 4, which we're actually demoing there at the booth. One thing that we are not demoing, but since you guys stuck around like stalwarts for sessions on Thursday, I'll give you like the secret poop. One of the things that is going to be in there is that there will be an official vTeleport. It will be a mass scheduler for VMotion and storage VMotion tasks. Because even though the demo that we did on stage was really cool, hey, move everything from Boston to Hopkinton, it's very like, wham, awesome sauce, right? In reality, that's not how you're going to do it. In reality, you're going to go, on Thursday, I'd like these 20 VMs moved, please, right? Do it on Thursday and then tell me when you're done, right? That sort of thing, right? So we're working furiously on that plugin. Now, the thing that I want to highlight here is, again, people come to VMworld to see not just the stuff that's GA, so all the stuff we've talked about so far, you could do tomorrow if you wanted, right? But what comes next? So, warning, warning, warning. Do not try this at home, right? I'm going to talk about all the reasons you shouldn't try it at home. It is not ready to use in this use case. Am I being sufficiently clear, right? So, I was, lucky enough. Our team's got I think a dream gig in the sense that, we were playing with, vCloud Director, boys, how long ago? Like the last 6 months, right? And we get to play with EMC toys, a year or 2 years before they appear, right? And the engineers hate us, right? Because we're always like, hey, cool, let's take that and run with it. So we persuaded them after a little whoop, whoop, to give us the VPLEX bits for a VPLEX Geo. I'm trying to make this a little fun and punchy because, come on, it is Thursday, right? We persuaded them to give us the VPLEX Geo bits hot off the presses, right? Literally like the first alpha builds, because we're like, wouldn't it be cool? How do we show kind of where we're going around this idea? And we did some tests. The tests were basically, we had 2 vSphere clusters with both LAN, latency simulators in the middle, and so WAN emulators, and also storage SAN latency emulators in the middle. And what we did is we said, let's dial up the crank until the whole thing falls apart, right? And find out what happens. So, this is what we ended up doing. The equivalent of Boston to Buffalo, and then Boston to Chicago, then Boston to Omaha, right? So longer and longer distances. Now again, it's not measured in distance, right? It's measured in latencies. So here's a mind-blowing stat for you. The way that we got these distances is we went onto the AT&T site that basically kind of gives you some latency estimations and correlates that with distance. But if you had dark fiber between the sites, the last one at 44 milliseconds of round-trip latency is the equivalent of going a third of the way around the world, right? So, 44 milliseconds with dark fiber is really, really, really far, right? So, let's take a look at what this looks like. I'll move the little mouse. So, this is what the VPLEX UI looks like. It's simple, it's easy, it looks like all of the new EMC UIs. We've converged the UIs because people have told us they want common look and feel. This is 2 VPLEX clusters that have got underlying storage that has created an asynchronous distributed volume, right? This is the latency simulator UI, and we've injected basically 14 milliseconds of round-trip latency. So this is Boston to Buffalo, roughly equivalent, right? So first test. Let's take this workload, which is an OLTP workload that's running, so it's up and running, and it's not lightweight, and we're going to VMotion it between these 2 data centers, right? Off it goes. There's a little bit of performance impact because, again, the data doesn't exist there yet, right? And in 5 minutes, we VMotion this 100 gig VM under load over 730 kilometers. So that's cool. So let's dial it up a little bit further, right? Let's dial it up to 10. 26 milliseconds of round-trip latency. Now we're moving it 1,600 kilometers, so Boston to Chicago. And we move that workload, off it goes. What's the performance impact? What's the latency impact? So there's a little more of a performance impact while it's going on. But, hey, we're still operating. It's doing it live. And 14 minutes, boom, job completes. Still amazing, right? So now let's dial it up to 12, right? So, boom, we're now at 44 milliseconds of round-trip latency. And if you take a look, let's do that same VMotion. Let's see what the impact is for the workload while it's running. Let's take a look at how long it takes. This is 2,300 kilometers, or if you have dark fiber, a third of the way around the world, right? Off it goes, and you can see that there's more of a performance impact. But again, we're moving a workload live over distance with no performance impact, with no downtime for that individual application. And it's going to take longer. Doesn't take too much longer. If we take a look at how long the overall process takes, is in 19 minutes we move the workload, right? And once it gets there, the workload climbs back up to its steady state degree of performance. So this is what you just saw. What you didn't see is we dialed it up to 80 milliseconds of latency, because that's what it took to go from Boston to San Francisco, and we're like, hey, we're in San Fran, that'd be kind of cool. At which point the whole thing blew up. So the things that I'd highlight is, number one, this is alpha code, number one. Number two, the engineering teams think that they can improve the performance impact, time to do tasks, all of those sorts of things. And we think that it can actually go over longer and longer distances. We're trying to figure that out. The other thing that's interesting is, the other reason why you should not try this at home is, this is so far out of VMware's support matrix and support position, which no one in their right mind should violate. So currently, what are the VMotion restrictions that are listed in terms of latency and characteristics like that? They're like 5 milliseconds. Like, there's a published KB article that says this is what you need to have if you're going to do a VMotion between sites, right? The one thing that's been interesting through the whole exercise, because we're doing this hand in hand with our peers and colleagues at VMware, is there's actually more capabilities and broader bands than people think. So if you are a reader of Scott Lowe's blog or Duncan's blog, there was a lot of discussion over what do you need to do VMotion? What layer 2 adjacency do you need? And the reality of it is, currently the support stance is very clear. You're on a single segment. But the answer, actually, you can use routable networks for VMotion and for VM networks. You should not. Just because you could, you shouldn't, right? So, again, it's just important. It gives you some ideas of what things are possible. The other thing is, one of the reasons that it failed at the end was obviously vCenter is having a dialogue with the VPXA agents, right, that are going on in the VM kernel, right? And there's all sorts of inter-cluster dialogue that's going on, right? And those things are designed today not for stretched cluster scenarios, right? Now, this is highlighting, though, that the possibilities of what's possible is much broader than a set of what customers can, should do, and what's supported today. Stick within the support boundaries. I promised VMware I would reinforce that until I was blue in the face. Sufficiently reinforced? Right, okay. So let's talk a little bit more about the things you need to know, right? And now I'm going to talk about back to the synchronous class use cases. Let's take ourselves out of the realm of, the future and bring us back squarely to what's GA supported and possible today. So if you're an engineer who's ever written a clustering thing of any kind, you know that the most horrific scenario is the split brain, right? And a split brain basically means that, there's a partition, and in the state of partition, both sides think that they're in charge, right? So, it's actually better to have one side go dead than it is to have both sides be live. Because if they're both live, they'll both change, and then when you try to connect them back together, you can never merge them. Does that make sense? So both at the VMware layer and at the storage layer, understanding partition behavior is very important. And again, sometimes storage vendors get way out over their skis by focusing on storage level partition behavior as opposed to partitioning both at the VMware layer and at the storage layer. Does that make sense? Because it's an integrated solution. So what happens with VPLEX if you have site partition, right? When you create a VPLEX distributed volume, what you do is you select a site bias, the preferred site. The preferred site is the winner on partition. This isn't done for the entire cluster. It's done on a volume by volume basis. So think of it as a data store by data store property. Which side is the winner if it gets cut in half? Does that make sense? So basically, on partition, if there's any loss of communication between VPLEX cluster 1, VPLEX cluster 2, anything that is the non-preferred site goes into what's called I/O suspension. So I/O suspension means that you can't write to it, but you can still kind of read it. It's still there, right? What that means is the data store doesn't go dead, but any I/O to it stops. Does that make sense? So what's going to be the behavior of the VMs? It's going to be interesting, right? What's going to happen is eventually the guest timeouts will be reached where they go, hey, I can't write to that individual data store anymore, and they'll blue screen, at which point a VMHA response will start, right? But the VMHA response will determine which node in the cluster can be retried, and it actually may retry one of the nodes in the cluster that still can't access that data store, right? So the VMs will just perpetually not be booting, right? And again, that's okay, because if they were booting against that side, they'd actually be booting. And what happens if it's not that the non-preferred side? This is a very important idea, right? You've got the preferred side and the non-preferred side. There's been partition. Does that mean that this site is a smoking hole? Or does it mean that your telecom provider has had a bad day? Or someone put a backhoe, and cut a cable, right? If they've cut the cable, the preferred side is still up, right? And the VM may be continuing to run over here, right? So it's important to understand that what occurs is that when any Site Recovery Manager customers, do you wish that Site Recovery Manager would automatically fail over? Anyone? That's the correct answer. You do not wish for it to automatically fail over. This is a critical moment where a human really needs to be involved to figure out, is this a smoking hole? In which case I can now, resume service for the ones that are, non-preferred in the opposite way. In other words, the analogy is in Site Recovery Manager, that's where the human hits the run recovery plan button, right? So it is possible for a human to intervene and say, I've determined that it is a smoking hole, remove the I/O suspension. Does that make sense? The other thing is that when you get the clusters communicating again, you don't need to do anything. The I/O will resume. So it's impossible to get in a split brain condition. Does that make sense to everyone? Right? Okay. Where are important pitfalls today? So the primary use case that we see customers deploying today is vMotion between clusters, not stretched clusters. And here I'm talking about VMware level stretched clusters, right? The one thing that's a caveat with that is that you can vMotion between clusters, but you can't vMotion between virtual centers or vCenters, right? So that's an area actually of work and research. How do we make inter-VC vMotion possible? That's also another important thing that's going to be required for vMotion in and out of public and private cloud models. Now, stretched clusters are actually supported by EMC and VMware today, but I'm here to try and convince you it's a bad idea, right? The reason it's a bad idea is that, first of all, you're going to have this behavior where the non-biased side, so in other words, the non-preferred sides, the VMs will freeze. They'll try and do a VMHA restart, but they're going to do it against a data store that looks like it's still there, but it's going to be in this perpetual state of trying to boot the VMs. The ideal behavior actually would be if the paths were just marked as dead. And that's something that the engineering teams are working on with VMware to change. To go, if it's VMware and you get an IO suspension, mark the path as dead, the data stores go gray as unavailable, and then HA doesn't keep trying to reboot the VM on that data store. Does that make sense to everyone? Right? The other one that's very important to understand is VMHA fundamentally was not designed for stretched clusters. Right? So everybody here I'm presuming everyone's relatively familiar with VMHA, right? So when you create the VMHA policy, you basically identify how many hosts are allowed to fail, right? And now in vSphere 4.1, you can basically say X percentage of the host, or I want to reserve this host to be the HA host. The thing is that in this case, you either need to disable the policy for the HA admittance policy. You know how the default is you're not allowed to put VMs on that would violate the HA constraints, right? That's how I find most customers outside labs tend to operate. In the labs, you're like, whatever. Oversubscribe the cluster if need be, but typically in production environments, I find, at least in my experience, most customers say do not violate HA constraints, right? The problem is that in this scenario, on partition, you're going to lose half your cluster, right? Which means you have to, in essence, disable, the HA constraints. Otherwise, you're going to have problems when you try and actually fail over. Some VMs won't start because they'll violate the constraints. The other thing is that VMHA has got an internal construct called primaries and secondaries, right? Generally unknown by many, and the primaries are in essence the voters that determine what happens when the isolation response kicks in. So each ESX host has got something where it's basically going, am I isolated? Am I alive? If not, what do I do? And again, that's one of those VMHA things where you can say, what do I do when I've got the isolation response? Do I power on the VM? Do I power it down? Those sorts of things. The key thing is that the primaries are the decision makers. How do you know that all of your primaries aren't all on one side, right? Does anyone know if there's a way to determine, how to create a preferred primary? Anyone? Any bold? No? That's actually a good. Oh, someone's. There's an advanced setting, which I'm not going to say, right? Because you should not do it, right? Where you can set a preferred primary, right? The reason you shouldn't do it, there's lots of good reasons you shouldn't use advanced settings that are not supported, right? Trust me. So the key thing here is that this is an area where we're like, look, this use case is going to start to become more and more prevalent, over time. So a lot of area of advanced R&D that we're working on with VMware, and we'll talk a little bit more as we exit the session. The next thing is people go, but aha, vSphere 4.1 has got DRS host affinity rules. Does anyone know what I'm talking about there? right? You can basically say it's the beginnings of the idea of like sub-cluster allocation. You can say move things around within these hosts, but never move them to this host. Well, it's not quite never. It doesn't govern VMHA response. It only governs DRS VMotion activity, right? So again, you can. This is an area where, because someone can do something in a lab and it looks wicked awesome and cool, right? And again, if your EMC sales teams come to you and go, "Look at this thing," we're here to educate, not sell, right? Scott Lowe did a good session on this, TA8101, where he went into lots of the do's and don'ts about how do you specifically set this up, et cetera, et cetera. I think it got repeated twice. It's not being repeated again, but it's good. If you're interested, you'll be able to get it online and take a look at it. So where are we going next? So I already gave you one tidbit, which is where in Q4 we'll be delivering this idea of schedulable mass teleportation. And by the way, even if you're not a VPLEX customer, but an EMC customer, this will be cool because you'll be able to do storage VMotions on a scheduled basis, which is a handy thing, right? The other thing that we're doing is we're working extremely closely with VMware engineering around how do we actually harden that VMHA test case. Like VMware is extremely focused on product quality, and the test harnesses that go in for arrays and stuff like that is a lot of heavy lifting, right? That we work hand in hand on as well. Currently, there's not a category in the test harness for a stretched cluster thing. You know what I mean? Like, this is a relatively new idea, right? So, we're trying to go, okay, what would the QA and test harness look like for that sort of use case if we really, really want to harden this and make it very official? What are the capabilities that are required and changes in how VMHA operates to make this underlying behavior easier, right? The other thing, of course, is that VMHA has got a very primitive mass restart, high, medium, low priority that you do at the cluster. Use cluster settings or use VM level settings. It doesn't have the very rich sequencing capabilities of Site Recovery Manager. Does that make sense? The other thing that's very important is in this async use case, what happens if it gets splinched? Right? In other words, what happens if, as it's moving over, there's partition? And it's kind of like not there and kind of not here, right? This is the downside of teleportation if you read Stephen King books, right? You come out and you're like missing your arm, right? So the question is in the synchronous use case, it's safe because the data is always on both sides, right? But in the async use case, how can we basically say, let the VMotion complete even though not all the storage is there? Maybe what we want to do is we want to go, when you hit that VMotion between long distances, maybe what you want it to do is go, wait for it. Okay, now VMotion, right? Because that way there's no splinching, right? And how do we communicate to the VM kernel in ways that doesn't exist now about where it actually is? Because currently it's in the data store, right? The data store now is actually in different places. Right? So we have to have some mechanisms for communications that don't exist today. The other thing that's interesting is, and Beth, when she was doing it with me last time, said, now I'm going to be the engineering VP, Chad. This is way out, right? All EMC technologies run on this common x86 storage engine design. We tend to develop our products internally within EMC as virtual machines throughout their development cycle, and then they come out in various different form factors, but they run all on x86. If you go to the hands-on lab, you'll see it's running on VPLEX VSAs. One thing that's interesting about that is maybe VPLEX in different forms of packaging and ways to consume it, is something that customers would want to see and try, right? But again, for the people that did go to TA TA8218, which was that session, you can see some of the stuff that Jay and Kumar were talking about, are exposed here in the actual stuff that's going on behind the scenes. They're not smoking something, right? The other thing is that if you want to read more, there's that KB article's got all the gory details about every test case scenario, what happens on various partition states, what do you do, all of those sorts of things. Scott Lowe has got the session that we discussed. Network requirements is a good blog post from Duncan on this topic about, what are the requirements for doing vMotion fundamentally. If you want to try it yourself at the EMC Hands-On Lab, you can go to town. There's a VCE reference architecture that shows this in practice. One vBlock to another vBlock with SQL Server, SharePoint, Oracle, Exchange, all being geographically distributed and moved around under load, right? So a good document that contains boatloads of information about mission-critical app behavior in this use case. If you want to see that VPLEX demo, 500 VMs over sync distances, you can see it there, and you can see more there. Now, there is one thing here that I think is a cool thing. We're very, very confident about this product. So for VMworld attendees only, if you go to the EMC booth, you can basically, there's a link that you can go and on the computers there, you kind of fill in your information, and we're offering to customers that meet the requirements through that process. They can play with it to their heart's content for 90 days. So it's a pretty cool thing if you're interested in this use case. So what I wanted to do is we've got some time. I'd love to hear comments, questions, thoughts. And of course, if you have to leave, then I totally understand that. But if not, shoot. And let's let customers go first, guys. The reason it can, right. So the reason that SRDF can basically, reverse sync, and bring up the changes is because that remote side, there's only one side that's read-writable, right? That's what I'm saying. How do you do that type of style, having VMs active on both sides splitting, then resyncing? The answer is we never will, right? One thing that we are doing some early interesting testing around is FT over stretched conditions, how that would work. But that is expressly rooted in that problem, which is if this side is here and this side is here, you can't both be active at the same time but different. Right? Any other questions? Mm-hmm. So you need to yell it. You need to yell it out. I'm sorry, I couldn't hear the entire. Mm-hmm. Yeah. So the question that we're, the debate and the discussion that we're having is, in essence, should there be a VMHA++, right? That has some of the more complex start sequencing capabilities of SRM, right, coupled with a stretched cluster that's hardened for this use case, right, and that then is basically simultaneously a disaster avoidance and a disaster recovery solution, right? Yep. Right. Yeah. I think that the reality is that both approaches are going to coexist. Some customers will fall squarely into your bracket, right, where it's a good way to approach both disaster avoidance and disaster recovery. Right? Disaster avoidance means I'm vMotioning it beforehand. Disaster recovery is disasters occurred, I'm restarting stuff, right? But again, what I want to say is, and reinforce, is I would strongly recommend staying squarely in VMware's support stance and giving us a little more time for future vSphere releases to harden that stretched VMHA use case, right? Now, we do have several VPLEX customers that have said, I hear you, I got it, I'm doing it anyway, right? And what they basically do then is that on disaster, they change the site bias, right, to bring up the data store. They pick up the phone and make sure that it's actually a smoking hole. Therefore, the VM isn't simultaneously running in two places. And then they're going and saying, okay, great, now let's just either script or manually restart the VMs on the recovery side. You got it. Yes. It's going to take a little bit of time, but yes, we want to always be supporting every protocol under the sun. So it'll come probably first in FCOE support, but we want to be able to support everything. I'm sorry, I didn't want to cut you off, man, but you know.
I just wanted to let everybody know that Scott's session is being repeated today.
Oh, okay, cool.
At 1:30, so if you want to go, it's through 1:31.
Cool. Thank you. Yeah. What's that? Yeah. So he's part of the vSpecialist team. Okay, great, guys. Thank you very much. Enjoy the final hours of VMworld 2010.